ingeniería el próximo año, física avanzada, y la Facultad de Ciencias Sociales aquí metida en el medio como puente. Entonces, aquí hay representantes de países andinos, Centroamérica, Pierre, nuestro conferencista de hoy, viene de Francia, de Lyon, todos hablan español, aunque la charla va a ser en inglés, y España también. Entonces, bueno, aquí estamos reunidos, Fran. Muchas gracias por estar aquí y esperamos tu salutación.
Isabel, muchísimas gracias. Bienvenidos. Bienvenidos a la Universidad Autónoma de Bucaramanga. Perdónenme que estaba teniendo dos temas más. Preparé unas palabras muy cortas porque en mi disciplina, que es la historia, pues nos gusta escribir. Entonces, pues ya que la agenda está tan intensa y que además la estuve viendo para preparar estas palabras, pues quería simplemente decirles que pues, es un honor para mí como vicerrector académico dar apertura a este encuentro de El-Bongó Physics aquí en la Universidad Autónoma de Bucaramanga. Extiendo mi sincera bienvenida a esta comunidad fantástica que configura el proyecto, a esta inusual mezcla de físicos y comunicadores sociales, de expertos en ciencia abierta y colaborativa, y por otro lado, de expertos en ciencia de datos, modelado computacional, astropartículas y física computacional. Gracias a ustedes por hacer posible esta alianza que siento yo que es inusual, y en ese carácter inusual tiene un poder que yo creo que ustedes están empezando pues a reconocer, y este poder implica también el poder de la alianza con estas 12 universidades latinoamericanas, 3 españolas y una francesa, si los cálculos es al revés, 3 francesas y una española. Bueno, muy bien, alegaré la Francia. Bueno, sí, listo. Muy bien, sí. Il faut essayer le français. Sí, moi je veux bien. Bueno, gracias además por haber seleccionado a Colombia para este primer encuentro presencial, según investigué, ¿cierto? Según tengo entendido de los integrantes pues, del proyecto. Y retomo las palabras de Luis, que me lo encontré en mi investigación en alguna entrevista, pues preparando estas palabras. Hablo conmigo. Apuntamos a construir capacidades en educación superior. Estamos impulsando la transformación de la educación superior en ciencias. No es poca cosa la experiencia de diálogo que estamos generando en Colombia en estas áreas. Cierro conmigo. Y me sumo a este último enunciado. No es poca cosa lo que ustedes están haciendo. La peregrinación que comenzó en la Universidad Antonio Nariño el lunes para luego hacer una parada en la UIS y hoy terminar en la UNAM, da cuenta de un recorrido fantástico y necesario que aspira a la creación de comunidades de investigación y de aprendizaje en física. Y la noción de comunidad, de esta comunidad que ustedes representan y de las comunidades que aspira a construir el proyecto, tenemos que celebrar. En tiempos en los que las comunidades científicas y políticas desafortunadamente tienden a ser más endogámicas, más umbilicales, autocentradas. Ver a comunicadores y físicos hablando da aliento en estos tiempos que corren. Así que muchísimas gracias por este esfuerzo maravilloso que ustedes han venido haciendo. Y son tiempos que corren en los que la generación de capacidades para democratizar el acceso para el aprendizaje y la investigación en física se enfrentan con marcadas brechas de género en las prácticas científicas, en el acceso y participación de mujeres en programas STEM. Enfrentan retos relacionados con las profundas brechas sociales entre las que se encuentra no solo la marcada distinción entre sectores urbanos y rurales, sino de desigualdad a recursos entre ciudades capitales y ciudades intermedias. Estos son los retos que ustedes enfrentan. Estos son los retos que El-Bongó Physics está teniendo en el centro de configuración de estas comunidades de aprendizaje y de investigación en física. Esta relación profunda entre inequidades sociales y acceso desigual a la educación superior y por ende a la formación científica es alarmante en América Latina y refuerza la necesidad de proyectos como este en el que ustedes participan. La tarea no es menor, así que el cansancio es maravilloso porque esta tarea que ustedes están haciendo es significativa, es sustancial por la vocación de encuentro entre diferentes saberes y por las brechas de género, sociales y rurales y urbanas que el proyecto tiene que tener, considero yo, en el centro de sus ocupaciones. Puentes en la ciencia. La universidad al ritmo que marca la ciencia. Este es uno de los lemas que se encuentran en la página oficial del proyecto. Gracias por tan adecuada descripción del tamaño del reto que hoy enfrentamos. La universidad al ritmo que marca la ciencia. Que a nosotros las universidades no se nos olvide eso. Que es la ciencia, no la preocupación burocrática, no la relación administrativa, sino la ciencia la que tiene que marcar el ritmo de las universidades. Así que me parece un recordatorio muy profundo. Un recordatorio que aquí en la universidad tenemos y hemos asumido como una tarea en acción, no como una realidad dada. Es un verbo, es un día a día. Es que la universidad siga el ritmo de la ciencia y no al revés. Entonces no lo vemos como una cosa que ya está hecha, sino como algo que tenemos que venir construyendo, como un trabajo por venir, desde las acciones que ustedes han venido conversando en esta semana y que cierran aquí en la UNAM. Así que mis deseos sinceros de una buena conversación de cierre que abre además con una fantástica conferencia de Frédéric, que hablen de física, de altas energías, de astropartículas, de geofísica, de física computacional, pero también, como lo señalan los objetivos mismos del proyecto, que hablemos de la promoción de educación digital y de ciencia abierta, de la necesidad de remediar en algo, las inequidades en términos del acceso a herramientas de formación científica, del fomento de estos laboratorios fantásticos, de estos Fab Labs y de la creación de comunidades plurales, abiertas, inquietas y rigurosamente fundamentadas, pero también creativamente dispuestas a hacer ciencia en colaboración. Necesitamos hacer más ciencia, necesitamos hacer mejor ciencia, necesitamos generar dinámicas de profundo impacto en nuestras comunidades de formación científica y comunicación de la ciencia. Y ustedes están acá, en buena medida, para hacer que esto pase y para hacer que esto pase más seguido aquí en América Latina. Muchísimas gracias. Gracias por la invitación de Isabel y de todo el proyecto de El-Bongó Physics a estar aquí brevemente en este espacio y les auguro pues de corazón una muy grata y próspera y creativa, como había escrito, sesión, que el cansancio de ahí tintico, porque lo que ustedes están haciendo es maravilloso y que este proyecto tenga un muy buen porvenir, que se lo merece América Latina, la física y la divulgación o más la comunicación de la ciencia en estos proyectos cruzados entre Europa y Europa. Muchísimas gracias. Gracias. Y ahora sí a lo que thank you for being here.
Buenos días. Es un placer y un honor de participar a este inicio del proyecto El-Bongó. Como yo no soy perfectamente fluido en español, entonces disculpe, pero voy a presentar en inglés. Switching to English, so Luis asked you to have a vision of how AI can impact our fields, especially so our computational fields, and we try to push this in the presentation. So I've done my homework of last day conference, so I have 5 seconds to capture your attention. So the question, the goal will be during this talk to try to answer AI, is it a trend or is it a buzzword? And we will see at the end if we have found the answer. So I'm Frédéric Mouël. I'm professor at INSA-Lyon. INSA-Lyon is an engineering school in France, so ranked among the best universities in France. And we have several laboratories also inside the university. We have 22 laboratories. I'm heading one of these laboratories. Laboratories are quite big in France. It's more than 100 to 200 or 300 of people. So in terms of topics, I'm working in distributed systems, especially in dynamic environments, so edge computing, mobile networks, Internet of Things, and embedded AI. So at INSA, I'm holding a share on edge AI. So it means I'm working on checking how at the border of the network in communication system, we can include AI and at what cost and is it feasible? So the lab I'm heading is the City Lab, so it's part of the telecommunication laboratory. We are working on radio communication system, networks, embedded and distributed systems, and with several use cases such as robotics and security and privacy. So it means we are in a connected world, and how do we connect, let's say, people with object, smart object, and let's say the mantra of the lab is reconnected society. So we are 115 members, 1/3 professors and researchers, 1/3 PhD student, and 1/3 assisting staff. We have something like 5.3 million people every year, and we are managing 10 years project or let's say 10 million euros. So during this talk, I will try to push first what is AI. So everybody is talking about AI, but the first thing we have to really spot is defining AI. What are the different classes in AI we have? What are computational models? Because in physics, but not only in physics, but in several fields, we want to model the real world, and it's a complex world. So we have several models to do that, and we will see what is the link between AI in computational modeling. We will try to see what are the impacts on research methodologies. Really, AI has changed a lot, different way of doing science. We will see especially one part that we use, that is, let's say, basic principles and basic tools we have finally for all the fields. We need to do some computation, so we need to have platforms for this, and we will see what are the evolution of these platforms. And finally, we will go for what are the future trends and what can we include in El-Bongó for this. So artificial intelligence. So I've taken, you know, as everybody, I've taken the Wikipedia definition. I have just refactored a bit the definition because it's not really, let's say, in the right order. So artificial intelligence is the capability of computational systems to perform tasks typically associated with human intelligence. So really, it's more than doing some computation. It means we want to do something that normally human beings are doing. So it means having feedbacks from the real world, the physical world environment, doing some reasoning, so having some data to process and reason on this data. Learning, it means from the knowledge we have acquired from the environment, we can learn something, we can do some task, we can act on the environment to solve issues, to solve problems, and so that we can take decisions. So really, if this is, you know, I have just a small capture to say this is me as a human being, and this is what we want to have a robot to mimic somehow what I'm doing. So if we want to summarize, in fact, AI is, I have an environment, I have an agent which is capturing data or interacting with this environment, and it can be feedbacks that are, let's say, total, but it could be partial, it could be also, let's say, with uncertainty, and then this agent can act on the environment and can also act on itself, because when you learn, it means you are modifying yourself. Okay, so this is the beginning of the definition. And what is also confusing in AI, when you continue the definition, you say, okay, but AI is also a field of research. Okay, so the first part, it was computational capabilities. So I mean, we go for the object we are working on, and here we say it's a field of research. It's like in physics when you say, yes, physics is a field of research, and you can have, for example, an optical system, and the optical system is the object we are working on. In AI, in the definition, both are mixed, in fact. AI can be the object of research and can be the field of research. So it means everything we are doing in this research field is also code AI. So I think the definition by itself of this domain is confusing. We should use two words to define this, but it's like this. So it means as a field of research by itself, we are developing methodologies, software to do all this stuff, meaning perceiving the environment, reacting, learning, etc. So when we talk about AI, be sure to know what you are talking of. So the field of research, or let's say the object by itself. So when you start to classify what are existing, let's say, approaches in AI, one way of structuring AI is to have a hierarchical classification of AI. So first, artificial intelligence, where you have perception, you have reasoning, etc., and also interaction with your environment. And we have one specific part, which is learning, which is really interesting a lot our community, because, for example, if we're in other community, for example, interface between human and machine, then we will go for the first part of artificial intelligence. But what we are interested in this talk is to work and to see the interaction we have with computational model. And so it means we would like to do machine learning. So you have machine learning approaches, so part of AI, where you can find several approaches. So decision trees, random forest, vector machine, clustering, Bayesian approaches, so statistical probabilistic approaches, etc., and some more learning. So you have several ways of doing machine learning, and so it lasts for almost 60, 70 years. And what is really trendy right now, inside these different machine learning algorithms and approaches we have, what is trendy is deep learning. Why? Because in fact, it has gained a lot of popularity because of results that were not expected. So in deep learning, in fact, the modelization is using a neural network. So as we have previously seen in the previous conference, the first one is the perceptron. And the goal is to have one neuron. You just send inputs, and you would like to have outputs from the computation that has been done. And in fact, if you summarize what is, let's say, issues to define this neural network is how many neurons, how many layers do we include, hidden layers, and what is the transition function we apply on each neuron. Okay? If you just define these two parts, you can define several kinds of neural network. And you have plenty of neural networks. So you can have the classical perceptron that are feedback neural network. So you include, let's say, an input, you propagate and you back propagate the information. You can have recursive, recurrent neural network. You can have convolutional neural network, autoencoders, transformers, etc. And each time it's always how many layers, what kind of layers, how many neurons, and what is the function I include inside my neural network. And right now, you know, it's just by experiments that we found that several use cases, several configurations of neural network are more fitting for different use cases. Okay, and the last trend you have in AI is generative AI. So generative AI is part of deep learning, so it's still neural network. And in this neural network, you consider several mechanisms, so transformers with mechanism of self-attention. So it means I'm taking information from the context to readapt my input and output. Diffusion, for which is a kind of autoencoders plus this attention mechanism, and adversarial networks. So here you are training a neural network against another neural network. So they train each others. Here in generative AI, you have this notion of when I'm including inputs, I'm generating outputs that were not defined previously. So that's why it's generative AI. And it means generative AI can generate everything you want. You know, so it's not giving you the truth or whatever you are expecting, but it's just generating from mechanism you have defined in terms of layers and transition function. Okay, so it's really important to have this classification in mind. And once you have, let's say, chosen your approaches, then you have several ways to train your model. You can have supervised training. Supervised training means you work on inputs and outputs. So for the input, in fact, you give data as inputs, and you also give insights, labels that are giving, let's say, instructions to your model, so that what is good and what is not good in terms of results for your output. So it means you have a way to supervise the training as a professor and a student. You can have unsupervised training, so it means there you give just the input and you expect the outputs to be fitting what you like, but you have no way of checking that it's good or it's not. So this way of training is very interesting in environment when you have no way of deciding what is good. And you have a third way of training a model, which is reinforcement learning. Reinforcement learning is when you have feedback from your environment. So you train, your neural network is acting on the environment. You have feedback from this environment. So it means you have a way to decide if the outputs you have produced are good or not. It is a reward function. And from this, in fact, you retrain each time. Okay, so that's particularly interesting for environments where you have a lot of dynamism in the environment, where you need to adapt. And this reinforcement learning could be supervised, semi-supervised, or non-supervised. So what is it useful for? Because we are talking about AI, but okay, what is the goal? In fact, we are these neural networks can be interesting for, let's say, several classes of use cases where you want to predict your environment. You want to have a behavior and to capture a behavior, where you want to simulate or optimize your environment. So it means your environment is very complex. You want to simulate and optimize it without doing by real. Where you want to sort your environment, it's somehow something you want to classify. Or your environment is something where you want to find something, to find patterns. Or you want to interact with your environment and act and do something on your environment. So you can find different use cases for all these actions that your, in fact, approach can do. So, for example, to predict, it's interesting for forecasting, weather forecasting, time series. You know, it's quite useful because, for example, IoT sensors are just delivering a time series, recommendation system, natural language processing. So this is a point you need to know. So when you are talking to ChatGPT, the first part of ChatGPT, so the natural language processing first part is just to predict the next token. So you just say A, and it predicts A, just to answer you, for example. And so it's not capturing anything else than predicting the next token. So when you're talking to ChatGPT, just realize that he's not looking for plenty of patterns first. You know, he's just saying, okay, you say A. Most of people say A to answer. So that's why I'm saying A. Okay, so prediction. To simulate, optimize. So right now, for example, you have interesting approaches to simulate very large and complex environments. So digital twins, for example, to represent anything, smart cities. For example, here you have a complex fluid motor, and you can represent it. The idea is to have a model that is representing it, and then to try to work on this to optimize it. Another point which is interesting, with AI, you need plenty of data. You can use AI to generate or to, let's say, add new data. So this is a point which is really interesting. In most systems, if you don't have enough data, you can generate new data to enlarge your data set. Sorting is quite classical. You want to classify or to cluster. So classify is when you know the classes and you just want to put things in boxes. And clustering is when you have an unsupervised environment. You don't know where to put things and you find what are the clusters. So what are the objects that are close together. Anomaly detection, for example, is also something very usual, usual use of AI. You have done groups and you want to find what are the outliers, so anomaly. Ranking is also a use case. Finding patterns. Finding patterns is quite trendy because it's for image recognition, it has been it's a visible thing. So when you have a complex environment, such as an image or video, it's not easy to find object in a video or to find a pattern. So, for example, movement inside the video. And neural networks are quite good for this because you can have, let's say, the first layers that are capturing what's inside you, and you can have in deep learning, you can have deep layers that are finding specific patterns. To interact is an interesting point. So you can have conversational agent. So this is what is trendy right now. So chatbot, ChatGPT, and all the different, let's say, models existing. It's just remember your chatbot is not talking to you. Okay, it's just predicting the next token. If you say, I want to suicide, say most of the time when people want to suicide, in fact, you should say no. Yeah, but you know, if you go with the right path, it's like this. But if you go the wrong path, you know, your chatbot can just say, okay, in your case, you should suicide. And sadly, it has happened. And so conversational agent, so it seems to be, let's say, funny, but it's more like this. It could be useful. So, for example, code generation can be done easily, and it's really well working. Or virtual reality, it's also very well working. And when you want to act on your environment, so you want your AI to do something in the real world, then in fact you can use it, and it is used in robotics to coordinate drones. It can be used in games. It can be used in autonomous vehicle. Okay, so it's working like this. Just remember that, you know, it could be a probabilistic. It's a probabilistic approach. So if you are expected 100% of a good answer, it's not working like that. Okay, so now it's time to go for computational modeling. Okay, so the idea is we have AI, we know what AI can do, and now we have another field, computational modeling, that especially we are doing in El-Bongó for physics. And the goal is to check, okay, what is computational modeling and what's the link between with AI. So computational modeling, the goal is to simulate a complex system. Okay, we have a system that is finally too complex to be modeled analytically, and we want a way to represent and work with this model. So the idea is we have the physical world, which is giving us, let's say, the truth in terms of facts, even if we don't have all the information, and we are modeling this physical world. So we have here, for example, a modeling of Indian people of the world. They were modeling the world with the turtle, with the earth on the turtle.
That's ChatGPT.
And this is a model of the model, because ChatGPT, I model this with ChatGPT.
Wow.
It's a model of the model.
Yeah, you can do that.
Yeah. And so the idea is that the system we want to model is too complex to be modeled by linear system. So we need to have a way to model a more complex system, and to do that, we want to check if, let's say, the non-linear model systems that we will establish will fit the physical world, and it can only be done by experimenting. So the idea is you go for the space that your model is covering, and you try to check if your model is well fitting the real world you are modeling. And so it means you play with parameters, you try to cover the space, and if you have, let's say, enough feedbacks, if it is enough covering, you can infer abstractions. You can infer operational theory. Okay, that's always what we do in physics, you know. And as soon as we have an experimenting with parameters that is not fitting the model, then we need to go for a new model, or to enlarge the model. So how to do that? In fact, you pretty well known these different approaches. We have the deterministic models, stochastic models, interacting models with agent-based models. We can do and combine all these different models. And when we don't have enough information, we are emulating. So we are using emulating models. So in fact, we reduce the space with different techniques, PTA, etc. The idea is to have a model which is a sub-representation of the real world, and it could be enough. So we have plenty. We have all these techniques we well know, and we have seen before. We have also the approaches we have in AI. So the goal is to check, okay, what can we do with this? So I see, you see, in fact, the interaction coming. So for AI, computational model, so for example, it could be AI, so it could be applied to different fields, and so physics, engineering, or plenty of fields, especially physics for El-Bongó. So we have this model representing the physical world, and the idea is to use AI. So the AI, normally you have your agent interacting with your environment. The idea here is to interact with this model we have established representing this physical world. And so what is useful for? Is useful for this part of AI, so reasoning, learning, problem solving. The idea is we have a model and we would like to reason on it. We would like to check if this model is well fitting. So as we have this mechanism of training, we can interact with the model, change the parameters, etc., so that it will better fit this physical world. So the idea is to have a better modeling, a better predicting. Okay, so quite classical. I guess you are using it. But the second way AI can interact with a computational model is to have this interaction, to directly interact with the physical world. Because in fact, when you interact with your model, it means you optimize the model, but you don't know if this model is well fitting, you know? But you can have feedbacks. If you have feedbacks from your real world, then you can improve the agent itself that is interacting with your model. And it's interesting because at this moment you are using perception and decision making, and then you can better experimenting. It's not only improving the model, it's improving the way you are doing science, improving your way of experiment, okay, to better deploy your physics experiments. So what are the impacts on our research methodologies? This is a very important point. We have not seen this coming. We were, scientists, and we were having one methodology, and we have not seen that. So it's an article published in Wired in 2008. So it's not, more than 20 years ago, saying, okay, this is the end of theory. We don't need to do theory anymore, okay? Because we have big data, so it means we have really plenty of data. We can automate this machine learning with AI. So all our simulation analysis can be done automatically, so that we can reproduce easily all our experiments. And if we do that, instead of doing our hypothesis, we can let the AI finding the hypothesis by itself. So to summarize, here is my data. Go and find what's inside. Okay, you don't need to think before to an hypothesis. You can let AI find the patterns inside the data, and so that infer for you what should be the model, the theoretical model behind. Okay, and it's working. And it's working. So we have this move from hypothesis-driven science to data-driven science. And plenty of researchers are doing things like that. And it's working. And at this moment, people are still fighting between hypothesis-driven and data-driven approaches. And this article has been published last year, showing still that it's better to have a mixed approach, mixing hypothesis-driven and data-driven approach. It's outperforming the existing models. So if you go for your hypothesis, you have a result. If you go for data-driven, you have a result. But if you mix both, you have a better result. So there's still place for theory. So this is a good point for us. And also, so benefits are, okay, we have benefits, but we have also limitation. We have this limitation, which is a neural network is a black box, okay? You have one function to define, or a number of layers to define it, but finally, right now, we don't have, let's say, this modeling of how it is working. So we'll go for later, but we know that it is black box. And so it means we can only play on parameters, but we don't know why. Let's say theoretically, it's working like this. As we are playing with data, the inputs include plenty of biases. And so is it really representative of the physical world we want to work on? And we do. Typically, it's depending on the data. So a lot of work on that. We have computational costs, so we'll go for that later. And we have also these ethical issues. So we are working with data, but let's say, are we allowed? Is it good to have data on everything, on every people, etc.? So plenty of issues about this. So it means right now having this approaches based on AI should be each time limited by these different points. Each time we have a results, we can go for these points and say, okay, is it okay? Yes, but this. So let's move on this point on, we want to do computational model with AI. It has a cost. It was in the limitation right before. And how has it affected the platforms we are using to do this? So we have also moved from high performance computing, so HPC, to HPCs. So why is it important to go for this? We are doing experimental research, and experimental research is really impacted by our platform. So it means it's building our experiments. So this is an article published, I think something like 20 years ago or 10 years ago, saying that for better or for worse, when we have a benchmark, it shapes a field. Okay, it has very interesting properties that everybody can compare the approach. That's the issue is, yes, for sure, the benchmark, if you have biases in the benchmark, you know, it's not really representing your real world. So at Carla last week, in fact, I had a talk with Katie from the Chameleon project, and the feedback was really interesting. Is when we do platforms, it's really for the better of the science, for all disciplines, for all fields. So when you are doing a computer or a distributed computing platform, it's not only for computer scientists, it's good for all the fields, it's good for everybody. And we have summarized this, so for better or worse, in fact, scientific instruments shape a field. So it's important to go for this. So even for physicists, we need to take care of our computing platform. So at the beginning of high-performance computing, there were supercomputers. So the goal was to have always more computing. Okay, bigger, always bigger. So we are right now at zeta-scale supercomputers. So it's a huge amount of operation per second that you can do. The goal of supercomputers is to analyze data on complex tasks. Really, you need to have complex tasks, because if you have, let's say, linear model, you don't need to have a supercomputer. Okay, so it's really on physics modeling. It's really on, for example, biological approaches, working on DNA, etc., etc. And what are the issues, the research issues we have? In fact, the research issues are to work on the operating system you have on these supercomputers, to schedule, to do paralleling tasks, because the goal is to perform well. Okay, so it's really a question of optimization, and it's quite costly in terms of energy. But right now, HPC are moving to HPCs. Instead of having one supercomputer, we have many computers, distributed platforms. And the goal is to have more data processing. So because we need to deal with still more and more data coming from, you know, internet, web, IoT, social networks, or whatever. And you need to do more processing. But finally, it's specific task. It's not that complex task, in fact. When you're doing AI, machine learning in AI, it's not that complex in terms of tasks you want to perform. So classification, training, reinforcement learning, you know, in terms of computation, you just have neural networks having a value, and you're just doing some, some multiplication, etc. So it's not that complex in terms of task. So research issue, finally, when you are going to distributed platforms, it's more on having this mathematical modeling to fit specific hardware that is optimized to do that in a very efficient way. So finally, when you go for your data centers with plenty of GPU, TPU, quantum processor, FPGA, it's because you have this specific hardware that has been optimized for arithmetic modeling. Okay, the issue is not on placement, memory management, moving your data, etc. It's okay, I want to do this matrix computation. Okay.
Sorry. This works, for example, for weather forecasting, predictions, and that kind of thing, because that those are very complex equations to solve. So this kind of infrastructure works for that also?
Yeah and no. So it means when your task can be easily splitted because your data is independent, then you can use it.
You can do this.
Yeah. But if you have data where you have a lot of correlations in your data or your task, it's not well working. FPGA or GPU, TPU, etc. If you have to move your data all the time instead of computing by itself, it's not the appropriate approach. And there's a third way also right now. We have also many computer platforms, distributed platforms, but that would like to do less data processing. So we have still this large amount of data, but we would like to perform very simple tasks. So we would love for signal denoising, regression, time series, etc. And they are very simple tasks compared to the previous ones. And here, in fact, the research issue we have are, again, to go back to this to this operating system, but as they are tiny sensors, we need to take care of how to do that in an embedded way, to orchestrate, and we include a new point, which is really the bottleneck of the approach. We include networks. Okay, in supercomputer, no network. In data center performing GPU computing, etc., you have InfiniBand, so the bottleneck is not the network. But here, you distribute and you connect with heterogeneous networks. So the bottleneck is there. And in terms of energy, it's not costly, in fact, because you use tiny devices and you do, let's say, few communications, so that it's less consuming in terms of energy compared to your supercomputer and your data centers. So this is a very interesting approach. The interesting approach compared to the previous one, because right now, because of climate change, we need to take care of this energy part. So depending on the task you want to perform, the goal is to say, okay, where do I need to compute? Okay, so as a physicist, you should have this question right now. I want to perform a task, but this task, where do I need to compute? Okay, because I need to take care of it. So you can perform the task in tiny devices. You can perform the task in mini data centers you have at the edge of your network, or in a data center which is, let's say, more powerful. You can go for the connection through your network, and at the end you can compute in large data center. And you have this location issue that is, popping in your computing, and it's affecting your performance. So it's affecting your performance in terms of accuracy of what you are computing, and also how fast you receive this result. And it's really important according to the use case you want. So if you want to do weather forecasting, it could be, I want to do weather forecasting, you know, for 2 next weeks, go for a data center because you will do plenty. But if you want to perform from your IoT devices that has been deployed in one specific location, you want to perform this forecasting in real time, just for a field, for example, then you need to perform this there. And it's affecting your energy you are using. Because if you go through the different, you know, connected data centers, if you are using tiny devices that are not consuming energies compared to big data centers, you have not the same cost in terms of energy. And I think for physicists right now, it should be a point. Do I need to compute? It could go through or not. So HPC can be seen right now as a continuum. It's a continuum computing. So you knew cloud computing, which is there. Okay, you knew edge computing, fog computing, but right now we have this continuum computing where we can decide where to compute. It's important because these different parts are evolving, really. So it means it has been published. So a few months ago, or in June, yeah, in June, a few months ago, they have included a computer inside a textile fiber. Okay, you know, in your shirt, you can have a computer in one fiber. And it's not, you know, a microcontroller doing nothing, you know, it's really performing AI, recognizing your human activity. Okay, at a nano level. And, you know, it will change the way we are doing physics. We have also these IoT sensors that are deployed everywhere. And right now they are moving to being mini data centers. It means all the sensors you are deployed everywhere, you coordinate themselves and they are computing. And it is not neglectable in terms of computing power when you have millions of sensors. The core internet is also evolving. So, you know, your routers, switch that are interconnecting everything are now going for being a computer that is computing. So we have new network card that include GPU where you can perform computing while at the same time you are communicating. We have also sensors that are doing this. And so I have just, let's say, check what are, let's say, the market tendencies. So it's prediction, so it's not mine. Okay, so take care. You know, always these kind of agencies, they are predicting plenty of things, and it's not really like that. But what is interesting is more to compare the trends. Okay. Whatever are the, let's say, the numbers. When you go for ambient computing, so that means computing there, the prediction is in 10 years, we will have, let's say, 400 billion market. Okay, this is prediction. And what is more interesting is if we go and compare to the development of data centers, you know, it's more than 10 times less. And if you go for huge data centers, it's let's say 5 to 6 times less. So it means the trend is instead of doing computing in very large data centers, it's to go more for the border of the network. Okay, I don't know if that's a good prediction, you know, but this is somehow where it's going in the market. So to finish my presentation, I would like to show you one project, Slices, a European project that is interesting in terms of platform. So Slices, it's the goal we are expecting as computer scientists that you guys, you physicists, with your CERN. You have one platform where you can do your science, and your community, you know, has all converged to have one, let's say, big scientific instrument. And for computer scientists, it was not the case. Okay, so we had no big instrument. And right now, so from some years, we are starting a project in Europe, which is exactly in the same program. So research infrastructure as scientific instrument is the same program as the CERN. So let's say the same funds. It's a long-term project where we have plenty of partners and countries, and the goal is to build a network of computers, for sure. And but the goal is to have this network as an experimental platform and to have this large-scale experiment. So the goal, what we want to achieve in terms of scientific goal, the question is there. We have actually a network, internet and the web on top of this, which is oriented on knowledge. The goal was to disseminate knowledge. That's great. And for the next generation of networks, the question is, can we have a networks of people, network of societies, okay? Not just exchanging knowledge, but, you know, exchanging behavior, interactions, taking care of each people, etc. And if we want to experiment this, we need to have a platform at a large scale where we can do that. And you know, for example, if you want to experiment on social networks right now, you can't. You know, you have to go for Google or TikTok or Instagram to say, please give me your data. But we have no platform to experiment. So the goal of this project is to have this large-scale platform. So that's our CERN. We will see if it is working in something like 20 years. So I'm still have time. Okay. So let's go on future works and to see how what are the, let's say, new trends and how we can integrate this in El-Bongó. In terms of research, so I've seen interesting talk at CERN where they are working on particle collision, and they are working with graph. And I was wondering if we can go with information theory and graph theory work on that.
We have a colleague in Toulouse who does that. Christophe Collard, we have contact. He's very interested in participating in general.
Yeah, so I think that's a very interesting also. Yeah. We have another thought that could be included as perhaps a module in El-Bongó, so working on explainable AI, because right now this is one limitation. As soon as we all use a neural network, you know, you have no mathematical models that can explain why you have these results. So two kinds of neural networks can be also very interesting to use. So pins that are physics-informed neural networks. So the goal is to have a neural network and then to let's say include the physical law and to check if the outputs are fitting the physical law, because your neural network, you know, just predict, so you can hallucinate and predict everything. but gravitation is gravitation, you know. So it's existing. So it's you take the outputs and you check the physical law. So it could be very interesting to use and to show to the students. We have also biological neural network, inspired neural network, spiking neural networks. That could be also very interesting to check if in physics it could be interesting. So the goal is to work with the spikes we have in neural networks. We have in last talk a list of possibilities in terms of collaborations, call for projects. So with, for example, PhD, with EcoSnor, EcoSUS, etc., and I added one more. So in Europe, we have also a COST program where we can build a network of researchers. We are starting right now, so with my group and several people, a group on distributed quantum computing and networking. So it could be interesting for some of us. In terms of lecture, we can modules we can include in El-Bongó. So I think in the HPC AI part, we will check how we can include a module, so 16 hours perhaps, on AI ethics, AI sustainability, to check the energy and CO2 cost of doing the computing. And we can also include also regulations, laws that are applied. So I don't know if you have seen that last week. They have decided in California to legislate about AI, and it's coming. It's coming. And in terms of platforms, we have several platforms where we expect to use HPC continuum illustrated on physical issues. But I think main point should be to use the platform we have in Latin America. So with the Scalac network. For the moment, so I've asked Carlos, we don't have APIs to interconnect the different platforms. And an issue and a good interesting point in El-Bongó could be to do these APIs to connect these platforms. Okay, we are at the end of the talk, so we go back to the initial question.
Your 5 seconds of attention.
Yeah, I think it's a trend. It's not a buzzword, especially because it's AI is a very valuable tool for us scientists, because we know how to use it. But I think it could be also frightening and conducting to plenty of, let's say, misleading behavior if people are not initiated to what is really happening inside your AI box, okay, and hallucinations, etc. And it's not, you don't have the truth in your ChatGPT. Okay, so this is my answer to the question. I hope it will generate discussion in our group. And that's it. Voila.
Thank you, Frédéric. Nice, very good. I really enjoy it. And we have, I think, some time for questions. Interesting topic, so you have any questions?
It's very interesting thought. I wanted to ask you about this slide where you put the physical world, the model that you predict, and the AI, and so the two pathways that you have presented. So, as you have mentioned, the combined strategy of what is data driven seems to be the best, but also probably the hardest to implement. No?
For sure. You need to have feedbacks. For example, you need to have feedbacks from the physical world. and it's very, let's say, time-consuming in terms of implementation of your experiment. And I think it should be combined. So instead of starting with this approach, it could be, the last approach you can use. I think the first way, and this is what we are doing right now, we are starting from existing data, modeling, optimizing, and then we can, face the experiment conducted with the real world to check if what we have modeled is right fitting. So we can do that from the beginning. I think when the cost of doing that is not too important. So when you have IoT environment, you deploy sensors, not too costly in terms of budget, but it's not also too costly in terms of programming a sensor. It's not the same as programming, a supercomputer. So I think for some kind of experiments, it could be done from the beginning. And when you have more complex model, first start by, let's say, the classical way, going for data, hypothesis, mixing both, and then checking, with the physical world.
And if I may, just a very brief one. I think we all understand very well the energy cost when you talk about HPC, just regular processors computing. But could you give us some sort of a hint of what is this extra cost from this AI computing that could make the larger difference?
In fact, it's quite difficult to predict. It's difficult to predict if your experimental settings will be costly in terms of energy or CO2. But we have platforms like Grid 5000 where you have watt meters, and when you run an experiment, you can check what is the energy consumed. You can also extrapolate, infer the CO2 cost. And it's also generating data that you can reuse to train a model that will allow you to predict what will be your energy cost for any kind of experiment. And from this, so I'm doing this with my PhD students for the moment. So when they start their PhD, I'm wondering them to track everything they are doing, so on their computer, on our data center, so that we can infer the cost of a PhD in terms of energy and CO2 to check if the science produced is, let's say, efficient. And from this data, we can infer what will be the cost for the next PhD student, according to the subject. If you work on AI purely, or if you work on sensors, it's not the same.
I could have more than one. First one is concerning, I'm trying to project myself into the El-Bongó activities. So there will be a first semester in which everyone will have some training in data science, so that they will not arrive completely lost in the second semester. But I think it's anyway important that we figure out what exactly will be the prerequisites that we will prepare for the second semester courses for those who are interested in this specifically. And the other thing is that from my previous experience in teaching, so if you have a student that comes within a project, it's very important for this person as an accountant. The girl has access to everything it takes. But when I have a student that comes for a few weeks for an internship, registered at the university only or at my lab, then nowadays, even if you ask this person to do a simple training on samples that can fit into a lab, but then the training is extremely heavy. It takes several hours even when they're doing easy things, so it's not doable. and getting them an account somewhere, and this person learning how to use this thing, the configurations, the protocols, even the authorizations, it often takes weeks, and it's a significant fraction of the training time. The best thing is that we prepare for that. But we think once, and we have a simplified protocol to help.
I totally agree. So at INSA, for example, for students during the first and second year of university, we have, let's say, basic tools. So Python, R, SciPy, NumPy, etc. So everything they need to, let's say, work on the data, on data processing. But as soon as they need to parallelize, to optimize the GPUs, etc., you go for the next level, and you need to have, let's say, operating system skills because it's tricky. And for the moment, I have no way to do that easily. You have this step.
Yeah. I'm really used to hear that because sometimes
and for students,
we don't see the last ones falling into this trap. We're even considering buying a small GPU farm in our lab. Disconnected from everything because of safety protocols, but in which we open an account there and we have some strings. But this is too expensive for El-Bongó as a solution.
I think CUDA is, let's say, the easiest way to go from the programming model to a distributed and parallelized model. But it needs some skills, programming skills. You go from data scientist to computer scientist, in fact. I have no real answer to this, except that I think in El-Bongó we should spot this in the data science module.
That is why we are forcing to have
to have
from just from the beginning.
Yeah, I think this is a right point because it is useful for the next advanced modules. And
especially that the students will not be in situ, so we cannot sit down beside them and we will.
They have an example here from Honduras. We got them. We go away.
I think for El-Bongó, we should start with one platform, for example, in Scalax, and let's push all the students there.
Yes.
Yeah. When you register a student to have an email, you should have an account with there also, and the tutorial directly.
Then apologies for missing the first part of your lecture. But when I read you were talking about the fact that neural networks are black boxes, etc. So as scientists, this is not so sorry. And but even naively, when my students do things, I ask them to do as much closer tests as they can figure out. And I think this critical thinking is important. I even have them to check at not only scores and things like that, but even the weights. How the weights
black boxes are not bad, when you're doing experimental research. That's the thing, you don't have the model, so black box, and you do experiments to have feedbacks to check finally what is the model we can go on. So there. The point is that this neural network, we have no mathematical modeling for the moment. But it's a field of research by itself.
Sure, but we can access things like we can have the weights within, and we can check whether distributions of weights respond to the thing. And this is what we need to teach the students.
Absolutely.
Because this people outside cannot do that.
I've proposed in a project a PhD subject, sadly has been not accepted, but it was how to explain this dynamism you have in neural network in terms of propagation, weight propagation, using virtual reality. Because finally, when you propagate inside your neural network, it has a cost. And if you can see from the beginning where it should go, in fact, you can customize your network before to compute. So, but I have no PhD student on that.
We
I have a subject.
need El-Bongó students to get masters and then.
Yeah, we can work on it. And it could be in collaboration with Los Angeles. We have colleagues in Los Angeles working on virtual reality.
Okay, I think we are running out of time. Well,
I would like to ask something more towards the experience of student, actually. Not so much on the technical level, but more on the applications that you can give AI. It led me thinking the last question that you said, because I couldn't be at the beginning of the lecture, but more on the use of it being a buzzword of a trend. So for people of maybe our younger generations, they use AI for mostly everything these days. And people of older generations that are new to the concept don't really know how to differentiate AI from reality. Us younger generations can probably easily tell it apart, but the older generations are really susceptible to falling for like AI videos of people and they think they're real. Or that could be used with scammers or stuff like that. So for
I think we have to do a difference between outputs of AI and AI model.
yeah, exactly. Because that's what I said, not so much on the technical level, because for example, us more focused on an engineering level of things, we can work on the applications and the uses we want to give it. And all about the developing that you were mentioning about those modules and other stuff that I'm not so much familiar with on the exact details. But I do think it's very important to encourage research on students, because as me, myself, a student, I am not so much familiar on those topics. Even I already studied a course of AI data science, I was still not familiar. Like the course itself is just one class. It's not enough to cover everything about data. And so, like what you said about it being a trend or a buzzword, that's what left me thinking. I think it's kind of a double-edged sword in a way that you can ask for like research purposes, study purposes. It's a really important tool. But for people of the common who are not really focused on our approach, they sort of a distorted reality in a sense, if I make myself clear. I don't know how to explain.
Yeah, I understand the point of buzzword for the public, because finally it's something that will that is trendy right now, but that will disappear in a few years. But we see new generations, you know, they have replaced Google search for ChatGPT or Claude or whatever. Yeah. So it's a, let's say, a trend for young people that to go for that. And what is annoying from my point of view is that as a scientist, we go inside, we can go inside to check how it is modeled, how it is generating, etc. But if you are just using it, you know, it's just like using your car. You don't know the mechanics, and when you drive, you need to have a license. When you use ChatGPT, you don't. We should. Oh, you know, we should. When I say license, I have to say education. So I mean having a module to teach you to use it, etc., etc. Exactly what we're trying to learn to drive.
But it's too late, you know.
This is really a good point. In let's say our computer science field, I think we are pushing technologies too fast compared to if we compare to legal field, or if we compare to medicine. Medicine, you know, you have to test during 10 years before to push and use let's say medicaments. And for us, we push technology directly and we just check what's happening.
We're the test subjects, essentially.
Yeah. As Google said, we are the product.
Exactly. Yeah. That's where they earn money. Just getting data from us, essentially.
Yeah. And that's why I try to push this for everybody to know what's behind.
Okay, we thank Frédéric again. Y tenemos
Sí, estoy intentando como...